And good morning, everybody. Welcome back to Calc 3. Plan for today is I have a quiz for you on Standard 8. And then after the quiz, we will start talking about Standard 9. We'll start looking at properties of the multivariable derivative. I've got my usual office hours this afternoon from 2 to 3. Tomorrow morning at 10, tomorrow afternoon at 1. And Wednesday, the hour before class. As a reminder, office hours are now, you can show up in person. So if you just want to show up and talk about some math, you're welcome to just show up. If you'd like to set an appointment, you can. If you want to meet with me, or if you want to come do a retest, you are required to sign up ahead of time. And as far as homework goes, Standard 9 will take us 2 classes. We'll finish it on Wednesday. So the Standard 9 quiz will be on Friday. But in the meantime, I posted some problems on Blackboard from the book. Does anybody have any questions or comments before we get started? So, what was it over there? Oh yeah. How does a mathematician keep the sun out of their eyes? Keep the sun out of their eyes. Keep the sun out of their eyes. They use divisor. Alrighty, with that, we're going to go ahead and do today's quiz. So go ahead and take about 10 minutes for this one, as per usual. And let's start with here this time. Here next. Thanks. We'll be back in just a second. Oh, by the way, I forgot to mention, this is actually just a plain old tangent plane. It's not a hyperplane, just because it's from R2 to R. Shouldn't actually change how you solve the problem at all, but just to see your way. go ahead and take a few seconds to finish up your thoughts. And pass your quizzes forward, please. Pass your quizzes in, please. Alrighty. So, last standard, in standard 8, we talked about what it means for a function to be differentiable and how to take derivatives of multivariable functions. In the next couple standards, we're going to be focusing on looking at different properties of this derivative, multivariable derivative, meaning what does it share in common with the single variable derivative from Calc 1, and what is some new stuff that we can talk about for the multivariable derivative that didn't necessarily have to correspond to something from the single variable calculus. And so, first of all, I want to kind of list a bunch of the properties that still hold true for the Calc 3 as opposed to just the Calc 1 derivative. And it's going to turn out to be the case that pretty much any Calc 1 derivative property you might remember, like the sum and difference rules, product rule, quotient rule, chain rule, etc., is going to have a multivariable equivalent. So let's write these few out on the first page. So the first one is going to be the sum and difference rules. Which for Calc 1 basically says if you take the derivative of the sum or difference of a bunch of functions, you can just differentiate each function individually and then sum or subtract them. Same is going to be true for multivariable functions. If f and g are functions from Rn to Rm, are both differentiable at a point A, then so is the function f plus or minus g, f plus g or f minus g. And it's going to turn out to be the case that the derivative of f plus or minus g evaluated at the point A is just going to be the derivative of f evaluated at A plus or minus the derivative of g evaluated at A. Which in Calc 1 said something like the derivative of x cubed plus x squared, that polynomial, is just going to be the derivative of x cubed plus the derivative of x squared. So 3x squared plus 2x. Here, this says if you're adding together two functions and you take the derivative of that sum, then the matrices you would get from taking each piece individually and taking their partial derivatives and putting it into a matrix, if you add those matrices together, you get the same matrix as if you just took the partial derivatives of the entire thing at once. Similarly, constant multiple rule is going to say that if function f going from Rn to Rm is differentiable at a point A, and K is any scalar value, then the derivative of K times f of A is the same as K times the derivative of f evaluated at A. In other words, constant multiples pull outside of derivatives. If you differentiate f of xy equals 3x squared y cubed, that's going to give you the same as if you were to take the derivative for x squared y cubed, get that matrix, and then multiply that matrix by 3. The more interesting rules, ones I want to kind of focus on in looking at an example here in a sec, are product and quotient rule, where the product rule says that if you have two functions, f and g, that are both functions from Rn to R, the first two rules could work for any dimension of inputs and output vectors, but product rule and quotient rule are going to be specific to functions whose inputs are vectors, but outputs are scalar values. And if you have two functions, f and g, going from Rn to R that are differentiable at A, and the derivative of f times g evaluated at A is going to be f of A times the derivative of g evaluated at A plus derivative of f of A multiplied by g of A. So the derivative of the product is first times derivative of the second plus derivative of the first times the second. Does that look familiar to anyone? Max, is this sort of familiar looking to you? Why is that? Yeah, this is the exact same formula in essence as the Calc 1 product rule. Derivative of product is first times derivative of second plus derivative of first times second, except it's just written with different notation that's more general, where this kind of works for functions from any Rn to R, and if n happens to be 1, meaning you're looking at a function that both takes in and spits out scalars, this gives exactly the Calc 1 product rule. Just a generalization of that. And similarly, for the quotient rule, again, if we have two functions, f and g, going from Rn to R, where g of A is not 0, the outputs are scalar, so just the plain old 0. If g of A is not equal to 0, then the derivative of f divided by g, evaluated at A, is going to be g of A times the derivative of f of A minus f of A times the derivative of g of A at A, all divided by g of A quantity squared. Same basic formula as the Calc 1 quotient rule. I'll give it to you in musical form. If f we refer to as high and g we refer to as low, then it comes out to low, 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 d high, minus high, d low, merrily, 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 low squared down below. It's the exact same formula. It's the exact same formula as the Calc 1 quotient rule, just generalized to being able to work for functions from any Rn to R rather than just being functions from R1 to R1. The only difference is here these values are not going to be single scalars necessarily like they are in Calc 1. They're going to be matrices. So I like the constant multiple. The sum and difference rules are pretty self-explanatory. The product and quotient rules I think are a little bit more interesting in how the multivariable versions work. So what I'd like to do is to look at an example of how we can use the multivariable product rule to help us find some derivatives. Any questions I should ask before I start erasing things and we go on to the next page? So let's look at an example. So I want to look at two different functions. F of x comma y equals e to the power of x times y. And g of x comma y is equal to sine of 2x minus 4y. And I would like to do is I would like to find the derivative of the function f times g, what we would get if we multiplied f and g together at an arbitrary point x comma y. And we're actually going to do this using two different approaches. Because it turns out there's actually two different ways that we can actually find the derivative of the product of these two functions. So what would be one way that we could actually go through and differentiate the product of f and g? Anybody have any ideas on like an approach we could take for how we could find this expression in general? Okay?
You can find the derivatives of f and g and then
Just take the derivative of f and multiply by the derivative of g? Is that something that's okay to do? Emily, you seem unconvinced.
I don't think you
Just doesn't feel right in your gut?
well, it's not a problem with the product. And we know the product will
Yeah. Turns out there's a couple ways we could do this. This is not one of them. Mainly because while derivatives break up nicely over sums and differences, just like in Calc 1 of multivariable functions, that's what the sum and difference rules say, doesn't work that way for products and quotients. It's the same, right? Just like in Calc 1, if I wanted to say f of x equals x cubed, g of x equals x squared, if I wanted to differentiate the product of these two things, f times g of x, I can't just differentiate. You get 3x squared times 2x. What I would have to do is either use the Calc 1 product rule or multiply them together to start with, which would give me something like 5x to the 4th, which is not going to be equal to the 3x squared times 2x we get if we differentiated separately. Does that make sense?
yes.
Common mistake. I'm glad someone suggested it so I didn't have to. So how could we find this derivative? We can't just find the derivative of f and the derivative of g and multiply accordingly. Also, another reason, by the way, this wouldn't work out is because the derivative of f and the derivative of g would both be 1/2 matrices. And you can't multiply a 1/2 matrix by a 1/2 matrix. The dimensions don't match up in the way they need to. Max?
We use the product rule, so say dx plus g dx.
Yeah, so you want to use the multivariable product rule. Sounds good to me. Let's try that out. So our first approach is going to be to use this shiny new product rule that we have over there. So approach 1 is going to be to use the Calc 3 product rule. So if we do that, we'll get that the derivative of the product, f times g of x comma y, is going to be equal to f of x comma y multiplied by the derivative of g of xy plus the derivative of f of xy multiplied by just plain old g of xy. Which, using what we know about derivatives, the derivative of g of xy is going to be a matrix with 1 row, 2 columns, and whose entries are going to be del g del x and del g del y. And similarly, the derivative of f is just going to be a 1 by 2 matrix whose entries are del f, del x, and del f, del y. So this is the expression that, this is a nice way that we can go through and find the derivative of f times g, is to plug everything into this multivariable product rule formula. Just like the Calc 1 version, the only difference is the derivative of g and the derivative of f are going to be matrices and not just single scalar values. So our f of xy is e to the x times y. If we wanted to differentiate g with respect to x, meaning we're taking the partial derivative of sine of 2x minus 4y with respect to x, so treating x as our variable, y as a constant, what would we get if we tried to differentiate g with respect to x?
Would it be 2 cosine 2x minus 4y?
I like it. 2 times cosine of 2x minus 4y. Where did this 2 out in front come from?
From the inside, taking the derivative of 2x and just treating 4y as 0 as a constant, so it's treated as sine 2x.
So it sounds like you're using the Calc 1 version of the chain rule here. Oh, by the way, I forgot to mention, there is a multivariable chain rule. It is complicated. It's going to get, standard 10 is all about the chain rule. So it gets its own standard. It's special. But if we're using the Calc 1 version of the chain rule, then differentiating sine of 2x minus 4y should give us cosine of 2x minus 4y. And then if we we have to multiply by the derivative of the inside function, 2x minus 4y, which if x is our variable and y is a constant, differentiating 2x minus 4y should give us 2 plus 0, which is 2. So that's why we have a 2 out in front here. Yeah, nice try. How about del g del y? Same function, g of xy equals sine of 2x minus 4y, but now y is our variable and x is a constant. Alan?
Negative 4 cosine 2x minus 4y.
Negative 4 cosine of 2x minus 4y. Indeed. Yeah, because just like before, we differentiate sine will give us cosine of 2x minus 4y. And now, when we multiply by the derivative of the inside, if x is a constant and y is our variable, the derivative of 2x minus 4y will give us a negative 4 that we need to multiply everything with. So that's our first expression. We get e to the xy times this matrix. Now we need to add, I'm going to go ahead and write g of xy out as just sine of 2x minus 4y times the matrix of partial derivatives of f. So what's going to be our del f del y, del f del x here? If we're treating x as a variable and y as a constant, what do we get when we differentiate this? Yeah?
Y times e to the xy.
Ooh, y e to the xy. Where did this y out in front come from?
If we're taking the derivative with respect to x, then y is a constant, and the derivative of y, x would be y.
Yeah, so it sounds like you're using this sort of, the derivative of e to the u is e to the u du formula, which is just the chain rule. And so we get back e to the xy when we differentiate e to the xy times the derivative of our exponent, and if x is our variable and y is our constant, the derivative of constant times x is just going to be that constant, so a y. How about del f del y? Sarah?
Wouldn't this be x e to the xy?
Yeah. Same reason as before, we'll get an e to the xy term when we differentiate. And now, if y is our variable and x is our constant, when we multiply by the derivative of the inside piece, derivative of constant times y is just going to be that constant. So x. Neato burrito. And now we're just doing stuff we did back in standard 5, I think. We just have a linear combination of two matrices. We can do our scalar multiplication, where we multiply each of the inside terms by the scalar out in front, and then we'll add together our matrices to get a single matrix as our final answer. So when we multiply the inside pieces by e to the xy, we'll get 2e to the xy cosine of 2x minus 4y. And then for the second piece, we'll get a negative 4 e to the xy cosine of 2x minus 4y. Our second matrix will give us something like what? Y times y e to the xy sine of 2x minus 4y. The second piece will give us x e to the xy sine of 2x minus 4y. And now we have two 1 by 2 matrices that we need to add together. This is going to be delightful. When we add the first components, we'll get 2e to the xy cosine of 2x minus 4y plus ye to the xy sine of 2x minus 4y. Negative 4 e to the xy cosine of 2x minus 4y plus x e to the xy sine of 2x minus 4y. And that is going to be our final answer. For the derivative of f times g, we get this 1 by 2 matrix, where this component is actually going to be the partial derivative of f times g with respect to x. And this component will be the partial derivative of f times g with respect to y. Ends up being a little bit nasty looking in the end. But where all of these pieces came from is just the multivariable product rule, where we took f times the derivative of g, where the derivative of g was this matrix of g's partial derivatives. And then we added the derivative of f times g, where the derivative of f was this matrix of f's partial derivatives. And we took all of our partials, combined everything, simplified down to a single matrix. That is what we got for the derivative of f times g. I said there were two approaches to take, and I gave our first approach, which is just use the Cap3 product rule I wrote on the board earlier. But there's actually another way that we could have found this derivative matrix. Anybody think of another approach we could have taken other than using the multivariable product rule that would have helped us to find the derivative of f times g, other than plugging in f and g separately into all these pieces? And so let's say we wanted to take the derivative of the function f of x equals x squared times x cubed. What would be your natural reaction to how you could differentiate that, to differentiate the product of x squared and x cubed? Avery? Yeah, something like this. I think the easiest approach is just multiply and then take the derivative. You can use the product rule too and say x squared times derivative of x cubed plus derivative of x squared times x cubed, and that would give you the same answer. But sometimes, in this case, for instance, it's easier to just multiply them together and then just take the derivative of the product directly. That's going to be our second approach that I want to try out for these two functions. So approach 2 is going to be to multiply and then differentiate. So the first thing we're going to do in the second approach is to just multiply f and g together directly. So that f times g of xy is going to be e to the xy times sine of 2x minus 4y. And that is going to give us a single function in terms of x and y, single kind of nasty looking function, that we should be able to differentiate. Because just differentiating here should give us the same thing as if we were to take the partial derivative of what's above, f times g, with respect to x, and the partial derivative of f times g with respect to y. Alright, this is going to have to go down a line, so because I need the space, plus x minus 2x minus 4. I'm just moving this down to here because I need some extra space to write. So now we can talk about how do we differentiate this lovely expression with respect to x. So we have a problem, and that if we want to differentiate this with respect to x, we're multiplying two different things, an e to the xy term and a sine of 2x minus 4y term. So what rule are we going to need to use if we want to differentiate this whole expression with respect to x? We're taking the product of two different terms with x's in them and differentiating. What rule are we going to need to use?
Doesn't it bring us right back to the product rule?
It does bring us right back to the product rule. But which product rule? The Calc 3 version or the Calc 1 version of the product rule?
Calc 1 version.
Yeah. We're going to need to use the Calc 1 version of the product rule to help us evaluate this. Because this is just a scalar value expression. If we want to differentiate this with respect to x, we could just do the first piece, e to the xy, times derivative with respect to x of the second piece, so sine of 2x minus 4y, plus the second derivative of the first piece, d dx of e to the xy, times sine of 2x minus 4y. And then we'll do the same for the derivative of this with respect to y. We'll end up with e to the xy times the derivative with respect to y of sine of 2x minus 4y, plus the derivative with respect to y of e to the xy times just plain old sine of 2x minus 4y. Thank you, registrar, for putting me in a classroom where the board is too small to fit everything I want onto it in a nice way. But essentially, we can differentiate f times g with respect to x and y using the Calc 1 version of the product. And now, if we multiply this out, we'll get e to the xy times derivative with respect to x. You all already found that earlier. If we differentiate sine of 2x minus 4y with respect to x, we'll get 2 cosine of 2x minus 4y plus derivative with respect to x of e to the xy, which is ye to the xy, times sine of 2x minus 4y, space, gap, meaning a big gap, because we're going on to a new entry in our matrix, e to the xy times derivative with respect to y, that was negative 4 cosine of 2x minus 4y, plus derivative with respect to y of e to the xy, well that's just x e to the xy times sine of 2x minus 4y. And would you look at that? We get a horrible monstrosity of an answer, but it's the same horrible monstrosity of an answer we got using the Calc 3 version of the product rule. So it turns out, if you want to multiply your functions together and then differentiate, you can to get the derivative of the product of two functions. Or you can use the multivariable version of the product rule where you split it up into all these different pieces like that. But either way, you're going to need to use the product rule at some point. In the first approach, in Ix's approach, we use the multivariable product rule to split everything up at the start like this. And then we ended up with a bunch of smaller matrices that we combined eventually into one big one. Or, using Avery's approach, we could just make one really big matrix right off the bat by multiplying our two functions and then taking partial derivatives of that. We're taking the partial derivatives of the product from the get-go involved using the Calc 1 version of the product rule. So question, did anybody prefer one of these approaches over the other? Either of these feel like it came out a little bit nicer, or a little bit less nasty, or made your head hurt a little bit less? Okay.
I preferred the second approach.
You preferred the second approach. Why is that?
It was a lot easier to just, well, the Calc 1 version was a lot easier because once you have, it's a simpler equation to start with, you usually multiply it. And I feel like it's a lot easier to use the Calc 1 derivative instead of finding the multiple matrices and adding them together and multiplying the matrices by constants. It's a lot.
There's certainly a lot fewer matrices going on here. We're able to do this one in fewer steps, I would say. Anybody else have any preferences? It's actually interesting, Dave, that you said you liked the second approach better, because my first class actually came to a consensus that they liked the approach number 1 better. And that they thought that splitting it up into smaller pieces from the get-go made things a little easier to keep track of than having to try and differentiate the entire products all at once. They said, oh, by splitting it up into these little smaller derivatives, that, yeah, there's more of them, but ended up being a little bit less, they said it felt a little bit more intuitive to them. And I was just curious to see what you all had to say, because I like both approaches. Well, maybe I should say this. I dislike both approaches equally. Because in essence, I think it's actually coming down to the exact same amount of work. It's just that in approach 1, you're breaking up that same amount of work into more individual steps, but the individual steps are a little bit easier. Whereas this one is, yeah, just breaking up these matrices. But in essence, you're doing all the same products and derivatives that you did in each step. In both cases, you're going to have to differentiate e to the xy and sine of 2x minus 4y separately, both with respect to x and with respect to y. And then you'll end up, in both cases, multiplying by f and g separately in different places. But in essence, it's the same amount of derivatives, it's the same amount of products. This one just breaks it up into multiple matrices, while this one just does everything in a single matrix. But in my opinion, it really comes down to the same amount of work.
Would there be any particular scenarios where one would be better to use than the other, or it doesn't really matter?
Absolutely. For instance, say you're looking at the standard 9 quiz and it says use the multivariable version of the product rule to differentiate the product of these two functions. Then approach 1 would probably be better. Practically speaking, not really. It doesn't really matter. Like I said, they're always going to be kind of the same amount of work, and so it really comes down to a matter of personal preference. That being said, I do think a very interesting quiz question would be something like, hey, here's two functions. Find the derivative of the quotient using the multivariable quotient rule. Now find it using the single variable quotient rule, and look and see that you get the same answer. That would make for an interesting question. Hint, hint, hint. But practically speaking, in the real world, there's no real reason why you would necessarily want to use one over the other. chain rule, by the way, there will be a reason to use one approach over the other, but we'll talk about that in the next game. Any other questions or comments before we move on from these rules? All right, so next, the rest is standard. I want to focus on the idea of what it means to take a second derivative or a third derivative of a multivariable function. So here's going to be the idea. So let's say we're looking at a function like f from R3 to R. And the function's f of x, y, z equals x squared y plus y squared z. We've talked a lot now about what it means to differentiate a function like this from Rn to R. We would say that the derivative of f is going to be a matrix with one row, 3 columns, del f del x, del f del y, del f del z, or if you prefer, f sub x, f sub y, f sub z. And if we write that out in this case, we'll get that our f sub x is going to be 2xy. Our f sub y is going to be x squared plus 2y times z. And our f sub z is going to be y squared. Just from taking all the partial derivatives. What do you think it would mean to try and take the second derivative of this function f? Like, just intuitively, any ideas for like what we could try and do that would somehow get us from just having things where we differentiated the original function once with respect to x, y, and z, to expressions where we can say, I've differentiated the original function twice. Al?
2y.
Say that again?
Would be 2y.
For here?
Yeah.
So what did you do when you get when you got to 2y?
Took the derivative of 2x, and then like took the derivative again.
Ah, so you differentiated this with respect to x, and you got 2y? Why didn't you differentiate it with respect to y and get 2x?
Because it's at the back.
Ah, because we differentiated it once with respect to x, so if we do it again, if we differentiate again, you'd like to do it with respect to the same variable. So it sounds like what Madeline's proposing is that she just took a partial derivative of the partial derivative. And in general, when we talk about finding second and third, etc. derivatives of a multivariable function, that's going to be what ends up happening, is we're going to take partial derivatives of the partial derivatives. So these are going to be called our first order partial derivatives. Is the fancy name for this. Basically saying we've differentiated the original function once. F sub x is when we differentiate it with respect to x. F sub y is when we differentiate it with respect to y. And f sub z is when we differentiate with respect to z, the original function. But you can do second order partial derivatives where we differentiate these new functions, because all of these are still going to be functions from R3 to R. All of these you could think of as being functions that take in an x, y, and z input and spit out the corresponding expressions. And the second order partial derivatives come from taking partial derivatives of f sub x, f sub y, and f sub z, respectively. So Madeline, it sounds like what you just proposed when you said take f sub x, differentiate with respect to x, is going to be what we're actually going to refer to as f sub xx. That means differentiate f with respect to x, and then do it again, differentiate with respect to x, which I will agree. What did you say we got for that?
2y.
2y? Sounds good to me. We're going to get 2y. We can also talk about what happens if we differentiate with respect to x and then with respect to y. We could differentiate with respect to one variable and then change it up and do it with respect to another. So just so it's clear, this means differentiate with respect to x and then with respect to y. WRT with respect to. So here, if we just look at this function, f sub x equals 2xy, if we were to differentiate that with respect to y, meaning we treat y as the variable in this expression and x as the constant, what would we end up getting? Ollie? We're going to get 2x. Derivative of 2x times, of constant 2x times variable y with respect to y, it's going to be just that constant, 2x. If we wanted to, if we're feeling a little bit frisky, we could even take the derivative of f sub x with respect to z. And what would we get if we differentiated 2xy with respect to z? Well, no z's to be seen, therefore the whole thing is constant and its derivative is going to be 0. So we just took all of the partial derivatives of f sub x, which itself was already a partial derivative of the original function f. We can do the same thing with the other partials. So if we were to take f sub y, meaning x squared plus 2yz, and if we were to differentiate this with respect to x, what would we end up getting? Bob?
2x.
2x. Oh, hey, that's the same thing as f sub xy. That's neat. How about f sub yy? Meaning f sub y differentiate with respect to y. Yeah?
2z.
2z. And finally, f sub y differentiated with respect to z. Wait, what would we get here? We took f sub y differentiate with respect to z.
2y.
And I get a 2y. And finally, we'll take our second order partial derivatives by taking partial derivatives of f sub z. John, what would we get if we took f sub zx, differentiating f sub z with respect to x?
0.
0. Oh, yeah, that's the same thing we got here for f sub xz. That's interesting. How about f sub zy? Benny?
I got 2y.
2y. Oh, hey, that's the same as f sub yz. That's interesting. How about the sleepy function? F sub z. Lindsay, can you give that one a go? 0. So it turns out, since we had 3 first-order partial derivatives, and we could differentiate each of these 3 functions with respect to any of 3 variables, we ended up with 9 second-order partial derivatives. By the way, we could keep going and take third-order partial derivatives if we wanted to. For instance, we could take the derivative of xy with respect to x, which is the same as saying, I want to take the original function, I want to differentiate with respect to x, and then with respect to y, and then with respect to x again, which is the same as differentiating this one with respect to x. So, Hannah, if we were to differentiate f sub xy, so 2x with respect to x, what would we get? just 2. Whereas, on the other hand, if we were to do something like f sub, I don't know, x, x, y, where we differentiated with respect to x and then y, so differentiate this expression with respect to y, Sean, what would we end up with? 2. Oh yeah, those are equal, and x, y, x, 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 y, that's interesting. So, if we had 3 first-order partials and 9 second-order partials, if we were to take every third-order partial derivative that we could, how many would we end up with? Huh?
27.
My favorite number, 27 of them. And then fourth-order partials, there'd be 81. Fifth-order partials, there'd be 243, etc. Every time we go up in order, we're going to have 3 times as many derivatives because we just take all of the previous partial derivatives and we can differentiate with respect to 3 separate functions. Any questions or comments about how we would actually go about evaluating these second order, third order, etc. partial derivatives? Sarah?
I guess, would you normally write them in this form, or, like, for me, this looks like something you can easily store in the matrix.
It does look like the sort of thing you could easily store in a matrix. In fact, I even made like a little 3x3 table of these. Coincidence? So if you flip to the next, thank you for giving me that up, Sarah. Turns out there's a special name for the matrix of all the second order partial derivatives. And for those of you who remember, well, you're all Hillsdale students, you all should know something about the history of the Revolutionary War and about how the Hessian mercenaries that we fought. Well, it turns out that the name of the matrix holding all the second order partial derivatives is called the Hessian Matrix. Named Hessian because it was named after German mathematician Otto Hesse, who's lived in the late 1800s. I don't know if any relation to the Revolutionary era mercenary group. But the Hessian matrix basically says if you have a function f going from Rn to R, it's going to be the n by n matrix whose entries are just exactly the second order partial derivatives. So I screwed up in the packet. What's listed in the packet is actually the transpose of what the actual Hessian matrix is supposed to be. So you might want to rewrite this over to the side. So top left entry is f sub x1, x1, meaning first variable, you differentiate with respect to the first variable, and then you do it again. Then going across the top row, you're going to get f sub x2, x1, meaning differentiate with respect to the second variable, and then the first variable, all the way over to f sub xn, x1. And then going down the first column, we'll get f sub x1, x2, all the way down to f sub xn, x2. F sub x2, x2, all the way over to f sub xn, x2, all culminating in the bottom right corner of f sub xn, xn. So I accidentally gave you what I have typed out in the handout, the rows are actually the columns, and vice versa, what they're supposed to be, so sorry about that. That's a Dr. Versal boo-boo. But if we go back and look at this function, for this example, I very specifically wrote out this table in this way, Sarah. Thank you for noticing my efforts. Because for this particular function, the Hessian matrix is going to have entries f sub xx, f sub xy, f sub xz, yx, yy, why oh why am I working on this? YZ, ZX, ZY, and then we could plug in using the exact same things you all found just a minute ago, and we'll get the 3 by 3 matrix of 2y, 2x, 0, 2x, 2z, 2y, 0, 2y, 0. And that is going to be the Hessian of this matrix, of this function f, going from R3 to R. It's just the 3 by 3 matrix whose entries are all going to be the second order partial derivatives of the function f. Yeah, questions or comments about what this matrix is or how we found it? Mm-hmm. Yeah, Jack?
If it doesn't seem to matter whether fxy and fyx, for instance, are the same, then as far as transpose versus the order that we corrected it to, why does that make a difference?
It's a good question. If you notice, when we went through and found these, at several points I stopped and said, oh, these things appear to be equal. That's interesting. Specifically, fyx and xy seem to give us the same thing, 2x. xz and zx appear to give us the same thing, which is 0. yz and zy appeared to give us the same thing, which was 2y. And I think as Jack is pointing out, one way we could interpret that by saying something about the Hessian matrix is that it appears to be the case that since it appears not to matter if we differentiate with respect to x and then with respect to y, or y and then with respect to x, it looks like the Hessian matrix is going to be equal to its own transpose. Where we haven't talked about the transpose in a while. If you remember back to standard 5, we said take the transpose of the matrix, you just swap its rows and columns. And if you notice, this matrix here, first row, 2y, 2x, 0, equals the first column, 2y, 2x, 0. Second row, 2x, 2z, 2y, equals the second column, 2x, 2z, 2y. Third row, 0, 2y, 0, equals the third column, 0, 2y, 0. And so we appear to have a matrix that is equal to its own transpose. I'll define this more formally later in the packet, but it's called a symmetric matrix. So the question I have for you, coincidence? And that's what we'll call it for today. So Wednesday's class, Jack, I'll kind of answer your question. It's going to turn out to be the case that sometimes the Hessian matrix is equal to its own transpose, which, by the way, is why I made that error. You're right, because usually they're equal. But they're not always going to be equal to each other. And on Wednesday, we'll talk about under which conditions do we know the Hessian and its transpose are equal, and how can we say something more general about the overall function in those cases. Yeah, that's a good question, though. Why does it matter? It usually doesn't, is the short answer.